Today we have several options when it comes to microcontrollers and development boards. We use them for lots of projects and it is very easy for prototyping our ideas. But it will come a time when your idea is settled, and you need to take that to next level. Although, lots of people use the development boards in their projects, usually this is not the case when we actually want to have our product in the market. For that, you will need to learn how to work with the ICs, and embed them in your designs to create a simplified product, which will implement only what is needed. Also, consider that you will optimize the size of your project using only the components needed for its normal operation. Otherwise, you would have a bulky development board, and a bunch of wires to connect the peripherals together. I am not saying you would never need to use the development board again. I still use them to write the code and for proof of concepts. Which is what the development boards are for in my opinion. For the phase 1 of your project, which includes code and proof of concept. Now, let's take a look at this project in the breadboard. This project uses an ESP8266 module, a shift register, a display and a BME280 temperature and humidity sensor module. There are push buttons to send inputs to the shift register, and be interpreted by the ESP8266 module. The shift register is there to add functions to the project as the amount of pins in the ESP8266 were not enough to add all the functions I needed. As you can see, I am not using any development board here. Instead, I am using a bare ESP8266 module PCB, and I have the minimum required discrete components to bring the module to a normal operation. Now take a look at the same project in a PCB. The left image is the bottom layer, and the right image is the top layer. The BME280 temperature and humidity sensor module would still be an external module, plugged in a female interface close to the ESP8266. You can see here that the size was optimized using the ESP8266 module instead of using a development board. Now I will go over some tips to have a ESP8266 IC in a breadboard. This will help you to understand what is required for the IC to work and what is needed in your design, if you plan to have a thin product in the end. If none of that, let's at least have some fun in the process. By the way, I will not go over the antenna subject for the ESP8266 as this is a video of its own, and the purpose here is to understand the IC in a bare format. Take a look at what I have here in my workbench. This is a fully wired ESP8266 IC. In the middle of the breadboard is the ESP8266 IC. For this, you will need first to have the IC soldered in a PCB adapter. I will use the QFN32 adapter from Full Stack Electron Canada like this one. I will add the link to it in the description. The IC is presented in a QFN32 package. But in fact, it has 33 pins as we will see later on. This adapter has 2 rows and 17 pins for each row, giving 34 pins. But the pin 34 is not connected. The bottom pad of the IC will be in the pin 33, and in the case of the ESP8266 is the ground pin. Along with the ESP8266 in a breadboard-friendly adapter, you will also need a flash memory IC. The ESP8266 does not have integrated flash memory like the ESP82A85. So, you will need to have one wired up in order to upload your code for the IC to run. Normally the ESP8266 modules in the market are shipped with a 4 MB flash memory IC. Another vital component for operation is a crystal oscillator which is all the way in the back of the breadboard. The majority of ESP8266 modules in the market uses a 26 MHz crystal oscillator. Although, a 40 MHz crystal oscillator also can be used. In order to upload code to the flash memory, we will need a programmer. I will use the USB to ESP01 programmer from Full Stack Electron Canada like this one. I will add the link to it in the description. This programmer is originally designed for the ESP01, as the interface matches directly to the module. But, it can be used to program any ESP8266 family module. This programmer has the automatic upload and reset integrated to its circuitry, which is a nice feature. It does not require any button or switches to move the module from programming to normal operation and vice versa. I will now use Arduino IDE to upload the blink sketch to the IC. You can see the blue LED will start to give us status of the operation. After the upload is done, the Arduino IDE will send a reset command, and the IC will reset and start running the uploaded code. Let's now get a few tips on how to make sure the IC and the PCB adapter is well soldered, and the pins in the PCB are actually what they need to be. I will not go over the steps of soldering the IC on the PCB, but this step is critical. I will not recommend you to use a soldering iron, because the pins are not really very well exposed. Besides, you will need to solder the center pin anyways, which is out of range of the soldering iron. That said, I will recommend you to use a hot air soldering station. They are not very expensive, and having this skills will really bring you to a new level of prototyping and designing your hardware. Let's first make a visual inspection. The visual inspection is quite simple and you would get lots of advantages on having a microscope. But, it can be done using magnifying lens. Here is a microscope view of the connections. We can see in this one the connections look quite good. You will need to train your eyes for this though. The clue here is the shiny solder connection in the pins. For this other image, we can see the difference when a dry connection appears. As you can see, it is very subtle and very easy to miss. That is why we also need to check with the multimeter. But, how to test if the pins are connected to the board as the pins has no exposed leads? Well, it is rather simple. In order to check whether all pins are connected to the board, you use each board pad resistance to the ground pad. You should have some resistance in all of them. Usually they are similar to each other with small variations. Here I have the board and a multimeter to perform the tests. You need to set the multimeter to the resistance function. In this board, the ground pin is in the pin 33. This is also true in the IC. As I said before, the IC comes in QFN32 package. That means, there are 32 pins in the 4 sides of the IC. But, for this specific IC, the pin 33 is under the board and it is the ground connection. One lead of the multimeter will go to the ground pin. The other lead we will use to step into each pin and verify whether there is any resistance, as so. This board passed our resistance test. But, we still need to perform another test before assuming the board is ready to be used in the breadboard. I understand it may look like it's too time consuming. But, I can assure you that this time spent will avoid some headaches, if you start working in a board not properly soldered. Now we need to make sure there are no bridged connections in our board. That could also be spotted in the visual inspection. However, this board has a pin under it, which is out of sight. So, before we plug power in our board we need to make sure the ground pin is not shorted with other pins. Especially if that pin happens to be the power pin. You need to set your multimeter to continuity function. That will sound a beep in case the 2 leads of the multimeter find none, or very little resistance when connecting to a short. Then, one lead of the multimeter you touch any pin in the board, and the other lead you touch the very next pin in the board. Like so. I accidentally touched the 2 leads of the multimeter here. That was not a short in the pins. You noticed I had a hard time to make the test, while the board was loose on the table. Another approach is to use a small breadboard and connect the board to it. That will give you more grip while performing the test. This board has passed the quality control. Now we are sure that any issue we face in the wiring to a breadboard would not be related to a bad connection in the IC but something else entirely. Now we are ready to start connecting this board to the required components. Let's now take a look of the schematics for our exercise. The ESP8266 Hardware Design Guidelines is the best source of information to gather what is needed to have the IC operational. I will highlight some pieces of the document, and that will be enough for our experiment. In case you wish to understand further, I recommend a thoroughly read of this guide. In the page 7, you will find the pin layout of the board. If you are using the PCB adapter from Full Stack Electron Canada, that will be a mirror of the pins on the PCB if you soldered in the right position. In the page 8 and 9, you will find a description of each pin. At the page 10, you will find exactly what you need to have the IC operational. Although it is a good practice to follow the advice from the manufacturer when you are building a hardware, we can do some compromises for the sake of our experiment. I did not use any inductor in the breadboard. But, be certain it will be part of my final design. I also did not implement anything related to the antenna. As you can see in the schematics, and without considering the inductors and the antenna, you will only need some capacitors, resistors, a crystal, and a flash memory IC. Now we have enough knowledge of the ESP8266 IC, and we will be able to integrate the IC in our designs to create something compact and efficient. Besides, the knowledge we gathered here can be transferred to different ICs for different purposes. I hope you found this video useful. And even if you are not able to follow along, you will be able to apply part of this knowledge in some of your projects.